This is another one of those videos where I'm going to try and give us some instructions for the day. I promise this one will be a lot faster than yesterday's. Today, the goal you can see here is to go over the math that is used to solve the base version of the Thanos problem. So again, a recap, there's a scene in the movie Avengers Infinity War where Thanos, the bad guy, throws a moon at Iron Man, one of the Avengers, and we're trying to figure out how that's possible. So the basic theory we're using is that let's try to make it as need to know as possible to make it as quick as possible. But basically, he has these stones that can control the universe. One of them is called the Space Stone, which he can use to like teleport around the universe and move through space, and it controls, the fabric of space, basically. And so when he uses that, it makes things glow blue, and the moon is actually glowing blue right as it's flying towards Iron Man. So we're saying that he changes G, capital G, the gravitational constant of the universe, to increase the gravitational force, and that actually allows the moon to fly towards Iron Man. We don't know if that's actually how he does it, but we're going to make that assumption that's how he does it. And we need to calculate, okay, what is the new G? How much did G increase in order for that to happen? That's the goal of the project, is find G once Thanos has turned gravity up a notch for the moon. So let's look at that math. Before we do that, let's make sure we know our goals for the day. So 3-step process. 1, watch this video. So you're doing number 1 right now. Good job. Number 2, check out the math on the next page and save it someplace safe for future reference. You're going to want to be looking at that while you write your script. And number 3, to get your points for the day, again, 5 points in projects, is give me a question, comment, or observation. So don't forget your exit ticket. And let's look at the math here. So we've got free body diagram for the moon. So the moon is the object that's flying towards us. Let's say we're fighting with the Avengers on the planet with Iron Man. So moon's flying towards us. The only force that matters is gravity, right? It's up in space. There's not friction or anything like that. It's a moon floating in space. The only thing that really affects things in space is gravity. So that's the only force. We've got gravity pulling the moon down towards us. Oh no, the sky is falling. Actually, it kind of is this time. So force of gravity between the planet and the moon, that's the only force. So pretty basic, simple free body diagram right here. Off to a pretty simple start. So force net, Newton's second law, is very important here. We look at the net force on the moon, and in this case, the net force on the moon is just gravity. There's only one force, so that is the net force. That's all of the force. Everything, the whole force is gravity. So F equals ma, that's what we started with. F net equals ma, and m being the mass of the moon. Since the only force is gravity, we can also set that equal to gravity. So that's what I did here next, is I set ma equal to gravity, g mm over r squared, r being the distance between the moon and the planet, mass of the moon, mass of the planet, and g moon. Because remember, g is not 6.67 times 10 to the negative 11th here. I think that's worth inserting a text box. It's still worth it. I know right now it doesn't seem worth it. G is not 6.67 times 10 to the negative 11th right now. That's because Thanos has used his Infinity Stone, his Space Stone, to change G. He has that power, as he's sort of a Titan. If you're familiar with mythology, Titans are a version of God. They're gods, not God. Sorry, but you know what I'm trying to say. He can control the universe such that he can change the force of gravity. So G is not 6.67 times 10 to the minus 11. G is what we're trying to figure out here. We don't know G. We're trying to get that. So first thing we can do, as usual, we can cancel out a mass. We've got mass of the moon. We've got mass of moon over here. So cancel those out. So what's left? What's left is acceleration of the moon on the left side, because all that was is ma from Newton's second law, and we lost the m. So all that's left is the a. On the right, what are we left with? We're left with G, capital G, of the moon. That Thanos has changed. We're left with the mass of the planet. That didn't cancel out, so we still need mass of the planet. And that distance between the moon and the planet squared. If you recall from the assumptions from the problem statement here, well, no, actually, I should bring that up. Thanos full instructions. Do assumptions. We have mass of planet because we assumed it's just like Earth. So boom, that's the size of the planet right there. We also have the distance between the two objects, between the planet and the moon. So we have some information here because of our assumptions. So back here. So we have mass of the planet. We have the distances. We don't know this. That's the whole point of the project, is to figure out this G moon. And we don't know this. So we need to figure out acceleration of the moon before we can figure out G. We need acceleration. Just like always, remember way back to like the second unit of the year, the motion unit, you need acceleration before you can find anything. Acceleration is a very key aspect of physics. So we need acceleration. Here is a kinematic equation, and that's the one we're going to use to find acceleration. We're looking for A right here. So we're going to go ahead and solve it for the moon. The moon is the object moving here, so all of this is for the moon. We know that the moon starts at 0. We're just going to say that. We know in the end it's moved this far. How do we know that? From our assumptions, right? The two objects started this far apart. So how far do they have to move in order to crash into each other? They have to move that far. So that's our x final. We're going to say, you know, the moon was nice, happy orbit, not falling, crashing towards the planet in the beginning. So in the beginning, the moon is not really moving towards or away from the planet. It's got a nice 0 velocity. It might be moving around the planet, but not towards it. And time is 10 seconds. I stole that from another video that was looking at this scene. You can measure a more accurate time if you want to, and then you'll have to recalculate the numbers, but just anywhere you have 10, replace it with your number. For some reason, I seem to remember lots of people calculating it between 8 and 9 seconds if you actually time it in the movie. Last year, I think several people calculated that. So say it was 8.7, anything you had a 10, just replace with an 8.7. So instead of 100, it would be whatever 8.7 squared is. So you can make this 10 more accurate. That's one way you can enhance your grade by adding some of your own math, is by changing the numbers to make them more accurate. That's something you can do. So anyway, we plug in what we know. We know x final, we know x initial, right? We're going with equation number 1 here from our kinematic equations. We know x final, we know x initial, we know v initial, we know t, not that it matters here because v initial is 0. 1/2 a, we don't know a yet. And t again, we know. So then we just do the math, right? 0 plus 0 is 0, so we can just ignore these two things. 10 squared is 100. So we get, 1/2 times a times 100. So now we need to get a by itself. That's the goal here, to get a by itself. So we've multiplied by 100. How do we undo multiplication? Division. So we've got to divide by 100. You can see I've done that here. And we've got to move this 1/2 to the other side. How do we undo a 1/2? The opposite of 1/2 is 2. The reciprocal, as they say in math, not the opposite, the reciprocal. So to undo a 1/2, you got to multiply by 2. So we multiply by 2, we divide by 100, and boom, here's our acceleration. So that moon is moving quickly, very, very fast acceleration, which makes sense, right? If you're going to get from the Earth to the moon in 10 seconds, there's a lot of acceleration involved, a lot of force involved, right? So that's the acceleration. We're done, right? No. Again, you got to remember your goal. The goal right here was g moon. So we needed the acceleration to find that. So now we need to take this old information, combine it with our new information, and we get the acceleration that we just calculated here is equal to, so we're going back to this equation right here. We just now, instead of acceleration, we have an actual number for that. So that acceleration is equal to g times mass of planet divided by distance squared. So I just plugged in the actual numbers here. Mass of planet, I put in mass of Earth. The distance between the planets, now that's a little trickier. Why did I add 3 numbers together? So let's go back to our numbers. The big number is still this one, the distance between the planets. But that's the distance between the planet's surfaces. That's how far the rocket would have to go if you blast off from the planet and land on the moon. Gravity does not come from the surface. Gravity kind of originates from the center of objects. So for the gravitational force calculation, we need to get to the center of those objects. So not only does it matter how much space is in between them, but it matters how much more do we have to go to get to the center of the moon, and how much further do we have to go to get to the center of the Earth. So that's why we add 3 numbers together. So we add the distance between the 2 objects plus the radius of the moon to get to the center of the moon plus the radius of the planet to get to the center of the planet. And that gives us our total gravitational distance. You can see that picture right here. Got a picture of it right here. The distance between them plus the radius of the moon plus the radius of the planet. That gets us our gravity force distance. So now we do the math. So when we add all of those things together, we get, I don't even know what that is, but let me find out. 392.5 billion, give or take, squared. So when we, and then we do all of the math to solve for g, right? So we've got these numbers here. It becomes an algebra, not even algebra really, a little bit of algebra, but mostly a calculator problem at that point, right? You could even just plug this right into wolframalpha.com. It would solve it for you. And when it solves it, you get that g is now equal to 0.1983. Compare that to what it usually is. It's usually, let's do it without scientific notation so we can get an accurate comparison. So times 10 to the minus 11, that means 10 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's what it usually is. This is what it is now. It's 0.19. It's usually 0.000000000667. There's not any zeros anymore. It's just 0.19. So last thing, actually, you know what? I'm not going to do it because it's another one of those opportunities for you guys to do a little bit more calculations, is by what percentage did G increase, right? It increased by, a huge amount, many billions of times. But how much did G increase? What percentage did G increase? How many times did G increase? Whatever you want to do, that's something you could calculate for, again, a little bit extra credit. And there's other things as well. In fact, I've always wanted to turn this into a calculus problem, and I think I finally will. As soon as I have time. Goodness, I hope I have time to do that today or tomorrow or this weekend. But I think I can turn this into a doable calculus problem without too much crazy calculus going on, actually. So those of you who have expressed interest in learning calculus, this might be the problem that we explore to do that. So that could be fun. It's something I've always wanted to do with this project. Now might be a good time to finally go ahead and do that. So that's the math. I have office hours again today. To join the office hours, again, you just go to the calendar portion of Teams. I can't show you my calendar because there's some confidential information on it, but calendar portion of Teams, to join office hours. What time is today's office hours? I want to say 1:30. That sounds right because I think my other meeting's at 2:30. So 1:30 to 2:30 is office hours, and then my other meeting starts right at 2:30. So I have to end right at 2:30, guys. And that's it. So let me know if you have any questions. Come to office hours if you have any questions. Paige has promised to show us her little reptile and rodent zoo. Basically, and fish and all sorts of things. She has all sorts of animals, so you can come and see some cute animals and get some assistance on the math of the Thanos project. So what do you have to turn in today? Exit ticket. Please complete the exit ticket and get that turned in for today's 5 points. And just, do you understand the math? Try to make sure you understand the math as well. That's another thing that I'd like you to try and do today. So if you're not understanding that math, come to office hours, get your questions answered. And I hope to see you there.